Hello, my name is Mireya Jurado, and today I'll be discussing some work done with Catuscia Palamidessi and Geoffrey Smith on a formal information-theoretic leakage analysis of order-revealing encryption. The motivation behind this particular type of encryption comes from our desire to store sensitive data in the cloud. We can't store in plain text since the cloud server could be acting as an honest but curious adversary, or the data could be stolen outright. But we can't use traditional encryption, since traditional encryption will prevent us from using the nice database functionalities that we would like to have, like searching and sorting. So in response, specialized cryptography has been developed that encrypts the data while revealing some property of the plain text so that we can use these database functions. This solution represents a trade-off between security and functionality. Some information is intentionally revealed in exchange for searching and sorting. The question we have to ask ourselves is it worth it? And if so, under what conditions? And we can begin to answer this question through the application of quantitative information flow, or QIF. QIF models a channel that takes a secret input X to an observable output Y, which could help the adversary achieve some goal with respect to X. We have two metrics to isolate the effect of the channel. The first is prior vulnerability, which represents an adversary's probability of success when she only knows the probability distribution on the secrets. The next is posterior vulnerability, which reflects an adversary's probability of success when she both knows the distribution on secrets and can see the observable output. We define leakage as the difference. In this work, we analyze two variations of order revealing encryption, or ORE. The first is ideal ORE, in which case no information about the plain text should be observable by the adversary except the underlying order of the plain text, which allows the server to perform range queries and sorting. The order of the plain text is equivalent to leaking an ordered partition of the column indices. Here in this example, we have a plain text column with numeric values. All that the adversary should be able to deduce about this column is that the contents at indices 1 and 3 are equal and less than the contents at index 2, which is less than the context at index 4. I'll refer to this example throughout the presentation. However, it seems that ideal ORE is difficult to implement efficiently. So cryptographers have developed a scheme that is efficiently implementable but leaks more. Named CLWW after the authors, this scheme reveals order and the index of the first significant differing bit between every pair of plain texts. In our paper, we prove that this is equivalent to revealing the first significant differing bit between the ordered blocks. And let's go through an example. So returning to our example, we can label the bit indices as follows, starting from the right as B1 and B2. Note that we have two different sets of indices labeled on this slide. The I indices represent the position in the column, while the B indices represent the position in a given number's bit representation. So from the bit representation of 0 and 1, we see that the most significant differing bit from the left is at position 1. And between 1 and 3, the index of the first significant differing bit from the left is at index 2. So in addition to revealing the order, the adversary can observe the index of the most significant differing bits between the blocks. For this work, we evaluate two different operational scenarios. The first is Bayes vulnerability, corresponding to an adversary guessing the entire secret column in one try. Given the observables, whether only the partition of blocks or the added most significant differing bit information from the CLWW scheme, our adversary will attempt to recover the plain text. We assume that the adversary knows the possible values as well as their prior distribution. For this work, we assume a uniform prior on those values. Before I show you some of the results, I want to point out that the calculations of posterior vulnerabilities are computationally challenging, necessitating novel combinatoric techniques that we describe more in the paper. So here we compare ideal and CLWW ORE under a Bayes adversary with 100 values ranging from 0 to 99. This graph reflects the best probabilities of success achievable by any adversary who only knows the prior and the channel output. We see for small column sizes, ideal and CLWW stay near 0, indicating that the adversary has a very small probability of success. But as the column grows, there's a greater chance that all of the values appear, making the task of mapping the ciphertext back to the plaintext easier. We can also see that for certain column sizes, CLWW performs worse than ideal, but generally they're comparable. In the paper, we proved a simple usage guideline. Namely, if the column is relatively sparse in that K is at least as large as N, then the posterior Bayes vulnerability of ideal ORE is very small. And here's the formal statement. The second operational scenario that we examined was bucketing vulnerability, in which an adversary wishes to guess the correct bucket of each index. One can think about salary information, in which an adversary is not concerned with guessing every salary down to the penny, but is instead satisfied with knowing the values approximately, where the level of precision is determined by the number of buckets. So given the observables and knowing the set of possible values, along with their probabilities, the adversary will attempt to guess the correct bucket for each index. In this example, a successful adversary will be able to identify that indices 1, 2, and 3 belong in the first bucket, while index 4 belongs in the second. When the number of possible values and the number of buckets are both powers of 2, this corresponds to an adversary who is guessing the number of bits of each secret value. I'll explain this more in a second. So here we compare ideal and CLWW ORE under a bucketing adversary. We set the column size to 1,000 with a number of values ranging from 0 to 1023, indicating a 10-bit secret. The x-axis reflects the number of buckets, and with 2 to the 10 number of buckets, this corresponds to an adversary wishing to guess all 10 bits of the secret, and then the first 9, and the first 8, and so forth. For ideal ORE, the adversary has a non-negligible probability of success when the number of buckets equals 2, indicating that she only wants to guess the first bit of each secret value. However, we see a different story for CLWW. An adversary guessing only the first 7 bits of the value will succeed with probability exceeding 97%. Because a bucketing adversary is so natural, we conclude that CLWW ORE is fundamentally insecure. Lastly, I want to briefly mention a simple mitigation strategy that improves the vulnerability of ideal ORE. Simply, the proxy responsible for encrypting can append randomly chosen bits prior to encrypting. One can still perform range queries by padding the bounds with 0s and 1s. This mitigation is transparent to the user, and it provably improves the posterior vulnerability of ideal ORE, although it does nothing to help CLWW ORE. So in this work, we provided a formal analysis of ideal and CLWW ORE through novel combinatorics. We established a usage guideline for ideal ORE under a Bayes adversary and showed that ideal ORE is robust under bucketing while CLWW isn't. Finally, we developed a simple mitigation strategy that improves the vulnerability of ideal ORE. Thank you for your time.